So the power method provides you the maximum magnitude eigenvalue and the corresponding eigenvector, as well as it can provide you the minimum magnitude eigenvalue and the corresponding eigenvector. In fact, we can still work around to find out the intermediate eigenvalues falling in between these two extreme values and the corresponding eigenvectors, or that also we can find out by tweaking this direct power method. So how we are going to do it? So let us see that. Before that, as we discussed that property, so if this is let me write it down here, and if this is the eigenvalue problem we are dealing with. Suppose if I add up, if you remember what we said is, if you add up some constant terms, so what will happen is a plus say some tau of I. So a plus tau of I vector into x will be equal to lambda plus tau of x. So what we found there is any additive constant to the eigenvalue will not modify your eigenvectors. Okay, so adding up any constant term will modify eigenvalue and the corresponding matrix, but your eigenvectors remain same. So we can use this property to find out. So what are the results we have? First one is we had the direct power method. So this gives us lambda max and x max. And the next we had inverse power method. And this gives you lambda min and x min. Now, if you wanted to get intermediate to these values, any lambda these values, we can use this property and find out. And that method is called as shifted inverse power method. Okay, so how we are going to do is, okay, fine. So let us start with our eigenvalue equation x. So fine. So now, so let us say the equation what we have, a dot x equal to lambda x. So, and the lambda values, let me write down, the lambda values are basically lambda min and go on up to say some lambda star. Okay, and then what we are going to get is something about lambda max. So now let me assume some constant, some number, let us say it's tau. So tau which is close to lambda star. The tau can be any number. So we will find out there can be one eigenvalue which will be close to this lambda star, sum of the lambda. So maybe here, so you take any tau away from lambda min and lambda max, the tau falls in between any of these extreme values, and it may fall somewhere else close to say some lambda star or some lambda x, whatever you call. We'll find out some number which is falling close to that. So this we call as a guess value of a certain eigenvalue. It no need to be exact. It should fall somewhere else in between this one. Fine. So then what am I going to do? I'm going to subtract this tau with this one. So what I will have, so this equation, I will modify it as a minus tau, tau is a constant. Tau I into x will be lambda minus tau of x. So this I will call it as, this I call as A shifted, because this is a new matrix, shifted matrix. That's what the same thing I am following. A shifted, and dot x equal to, this is lambda shifted into x. And this is a very, once we get this equation, so we can proceed further to find out find out the lambda star. How we are going to proceed further is, suppose if this is again eigenvalue problem. If I solve this eigenvalue problem by the inverse power method, so what it's going to give me is, this will give me lambda shift minimum. So now, what is the lambda shift minimum if you see? So this lambda shift is nothing but, nothing but the actual lambda of my original matrix minus tau. So, and when you do this, so then what we are going to have comparatively, so because of this, the lambda shift eigenvectors will be lambda min minus tau, it goes on, lambda star minus tau, it goes on, and lambda max minus tau. And if you see in this, since you have subtracted it, the minimum magnitude eigenvector will be this, because lambda star and tau are very close by, because that's what our guess we took. The tau we took, whatever the eigenvalue falling close to the tau, this will have the minimum value, and whereas other guys will be having a larger magnitude. So then what this is going to give me, the minimum of the shift when I do that. So then when I take the lambda shift minimum, so and if all I have to do is, after getting this here, my lambda star is equal to lambda shift minimum plus tau. So this will give you, so this will give us any eigenvalue in between the lambda min and lambda max. And of course, the x will be we have found that the x is not going to change, the eigenvector is not going to change, and we get the eigenvector also. By this method, we can find out, by using these power methods, we can find out lambda max, lambda min, and any lambda star falling in between them both, as well as the corresponding eigenvector. So this is the very simple and very power means, in fact, these are very useful methods to find out the matrix eigenvalues of a matrix. The only condition is the eigenvalue should be non-degenerate, and most of the cases that's what your physics problem when you frame it, that's what you look at. Okay, even though if you get a degenerate eigenvalues, and you have to that may happen because of the ill-posed problem. You have to properly modify the problem, then you can get into an discrete eigenvalues, and then you can solve this eigenvalue problem using this power method.